Good morning, everybody.
Good morning.
Good morning, sir. Good morning, sir.
Okay. So could you please switch on your video for a few seconds? Please switch on your video. Okay. Everybody, please switch on your video. Okay. Thank you. You can now switch it off. And let's begin. Can you see the screen now?
Yes, sir.
Yes, sir.
Okay. So I think in the last class we had talked about at the end the differences between that exist between geostationary and geosynchronous satellites, and how from Kepler's third law we could find out what are the factors which differentiate a geostationary satellite from a geosynchronous satellite. And as an example, we had considered the Indian Regional Navigation Satellite System, IRNSS, and we had seen that it is a constellation which comprises of both geostationary satellites like these ones, which are on the equator, geographic equator marked by the green dash and dots, and as well as other satellites, geosynchronous satellites, which are off the equator. Okay, because as per the definition, we have seen that the orbital inclination of a geosynchronous satellite is non-zero. Okay, that means the orbital inclination being the angle between the equatorial plane and the orbital plane of the satellite. That is usually non-zero for a geosynchronous orbit. And for a special case where you have this orbital inclination equal to zero, then that is a geostationary satellite. Now, moving ahead, the next important thing to understand is that when we are trying to establish a satellite communication link, okay, like say for example, let us take the very general situation. That means in a crowded room, you are trying to speak with one person. Then usually if there are lots of noise around, then uh, you have to turn towards that person and speak. That means the transmitting as well as the receiving systems, they should be more or less aligned uh, along a particular direction, along the same direction. So for that, it is important that you know, suppose who is calling you from which direction. So you turn towards that direction and reply to that person. So just like that, in case of a satellite also, we should understand that the transmitter is on board the satellite. Okay, that means we, as an user, we are trying to receive signals which are transmitted from the satellite. Now, of course, that information which is on board the satellite is most often not generated within the satellite itself, but is uploaded to the satellite from another ground earth station. Okay, that means the primary source of that information is usually another Earth station, which may be thousands of kilometers away from the designed or the designated receiver of that signal. So that means one has to, as an user, when you are trying to receive the signal uh, at a point on the surface of the Earth, you have to know the direction towards which your receiving antenna should be pointed. Okay. So for that, it is important to know that what is the location of the satellite with respect to your location or with respect to a standard coordinate system. Now, the most common and the standard coordinate system which is used in case of satellite communication is known as the geocentric equatorial coordinate system. Okay, the geocentric equatorial coordinate system. Let me see if I can. So the geocentric equatorial coordinate system, it is something like this, that like every coordinate system has to have an origin. So the origin of this geocentric equatorial coordinate system is at the center of the Earth. And the z-axis of that coordinate system coincides with the Earth's axis of rotation. We know that the Earth rotates about a certain axis once in 24 hours, a little less than 24 hours. So the axis of this geocentric equatorial coordinate system has to be aligned with the Earth's axis of rotation, and it passes through the geographic North Pole, okay, of the Earth. Then the x-axis that points towards a fixed location in space, okay, and that fixed location is once again something, because you see we are trying to establish the coordinate of a point or an object in the sky. That could be here, that could be there, anywhere. Okay. So that is why it becomes important to specify the reference directions in such a way that they have an universal understanding. It is not that India will define one kind of reference for the coordinate, some other country will define another kind of reference, not like that. It should be a kind of a uniform and universal. That means anywhere on Earth, anyone will understand what is meant by the coordinates of this particular satellite. So that is why the second direction, the second axis, this points towards a fixed location in space, which is called the first point of Aries. Now, for some of you who are just a little bit, curious to know that Aries is actually the name of a constellation, an assembly of maybe stars and planets in the sky. So, the first point of Aries is like on the day of the vernal equinox. Okay, we know that in an year there are 2 equinoxes and 2 solstices, right? The vernal equinox is around 21st March. The autumnal equinox is around September 23rd, while the 2 solstices, the summer solstice is around 21st or 22nd of June, and the December solstice or the winter solstice is around that date in December, like December 21st or 22nd of December. So on the days of these equinoxes, we had learned from our geography classes long back that we usually have equal duration of day and night. And thereafter, the sun tends to move towards one of the hemispheres, either the northern hemisphere or the southern hemisphere. Like after this autumnal equinox this month, which will be around say 21st of September, so few days from now, the sun will start to move towards the towards the southern hemisphere, so that the days will become shorter in the northern hemisphere and the nights longer. And just the reverse thing will happen in the southern hemisphere of Earth. So this first point of Aries is defined in this fashion, that if you join the center of the Earth with the center of the Sun on the day of the vernal equinox, okay, then that direction points towards the first point of Aries. Okay, so the one of the axes of this geocentric equatorial coordinate system is coincident with the Earth's axis of rotation and passes through the geographic North Pole, while another axis, it points towards the first point of Aries. So once you fix the two axis directions, the third axis, the y-axis in this case, that will be simply mutually orthogonal to both of them. So with that understanding, the geocentric equatorial coordinate system has been designed, and in this coordinate system, this coordinate system is used not only for satellite communication, but for other kinds of radio astronomical observations also. That means, suppose you want to fix the location of a star in the sky, or a planet, or some other celestial object, then also we use this particular coordinate system. And the coordinates that is used in that case is, of course, different from what we use in case of satellite communication. Like right ascension, like one of the coordinates that is sometimes used is known as the right ascension. So what is the right ascension? It is the angular distance which is measured towards the eastward direction, say, in the equatorial plane from the x-axis. That means, suppose this is the location of your object in sky, whose coordinates you want to determine. So you join the center of the Earth with the center of that object, and you drop the projection of that on the locally horizontal plane. The local horizontal plane comprises of the xy plane, because the z-axis is vertically upward. It extends through the geographic North Pole. It coincides with Earth's axis of rotation. So the local horizontal plane, it is this xy plane. So you drop the projection of that object on the local horizontal plane, and you join that with the center of the coordinate system, which is the center of Earth. So then, if you measure the angle from this direction of the first point of Aries, then this angular displacement is what is referred to as the right ascension. And in addition to that right ascension, you also need to point out, that means this will give you some kind of an idea, that is, this right ascension will give you the idea, that is, in which direction I should be pointing. Okay, suppose you go to the roof of your building, okay, and you have heard some noise from maybe a helicopter or something, and you are curious and you want to take a look at it. So you went to the roof of your building. So first of all, you have to understand from which direction that sound is coming, whether it is from the north of your building, the south, the east, or the west. So you turn towards that direction. And then, of course, because that helicopter or something else is in the sky, so you have to look up. That means you have to look towards the sky. That object cannot be on the ground level. So that angle is this delta or declination. That means you first turn your head in the direction from which you are hearing the sound. Either it could be north, south, east, or west, any direction. So that gives you an idea about the right ascension. And then you look up so that you reach the particular object direction. So then once you look up in the proper at the proper angle, you can visualize or you can see that particular object. So that is more or less the kind of simplified picture that I want to give you. Then there are also nodes. That means all these objects, they are moving. If they are moving, contrary to a geostationary or a geosynchronous satellite, if these objects in the sky whose coordinates you want to determine, if they are moving, then you can understand that they will penetrate the equatorial plane at 2 points, once while moving up through the equatorial plane, reaching a certain high angle, and then once again moving down to that other side. So it is just like something will rise up from one of your horizon, will reach a point in the sky which is high enough, and then set at the other horizon. So that means it will, in case of nodes, this definition is a little bit more extended and does not only consider your horizontal plane. That means the plane which you can visualize from your location along a particular horizon. But instead, it includes the equatorial plane. So the satellite will move up through the equatorial plane at one of the nodes, which is known as the ascending node, and it will move down through the equatorial plane at the descending node, the other one. Now, in case of this space communication or satellite communication, because you see nowadays satellite communication does not only mean that receiving these direct to home television channels. We are no longer limited to that only. Other than internet and voice traffic, there is also another very important application nowadays, that is communicating with satellites which are in deep space mission. Okay, deep space. They are not only confined to orbits like 20,000 or 40,000 kilometers around Earth, but they are kind of moving out or going deep into our solar system. So for those satellites also, you need to understand the status of the different subsystems of that satellite, how they are functioning, whether they are functioning properly or not. And if they are not functioning properly, then using some ground control commands, you can sometimes rectify that error. Okay, because once you launch a satellite, all your options of physical intervention to repair the satellite subsystem is gone. Okay, except in very rare cases like the International Space Station. You might have seen that in the newspapers, that sometimes the astronauts, they go up to the International Space Station to repair or rectify some of the faulty subsystems. But other than that very rare case, most of the time for the other kinds of satellites, that option does not exist. So in case of communication with any of the satellites, say for example, this three different categories of satellites that we have considered so far. Okay, can you quickly calculate what will be the round trip travel time of any command or any signal transmitted from Earth? It goes to the satellite, and the satellite subsystem automatically responds and sends back that information. So can you quickly calculate for each of these three categories? Like for the low Earth orbiting satellite, it is 1,000 kilometers. So what will be the time taken for a signal transmitted from the surface of the Earth to be received and then retransmitted back? Just calculate it quickly.
Sir, about 6 microseconds.
For which one?
Low Earth orbit.
6 microsecond. How did you calculate that?
Sir, twice the distance divided by speed of time.
Twice the distance. So it is like 2,000 kilometer divided by
The speed of light.
the velocity of light. So the others also, please try to calculate this. And for the other two categories also. So I could say the round trip travel time so that is about who was that who gave me that answer?
Chiranka.
Okay, so let the others confirm this. The
Sir,
round
it's
trip,
around 6.6 microsecond.
how much?
6.6.
Okay, your name please.
Sir, I'm Shoptarshi Ganguly.
Okay, so it is like 6.6 microsecond. Okay,
My answer is
Sir,
6.6 millisecond.
millisecond. Okay,
6.6
I mean,
microseconds,
yes.
sir.
No, it will be millisecond because
It is
it is in
millisecond.
kilometer. It is in kilometer. I made that mistake.
so be careful.
Yes.
Sir, for geosynchronous, it will be 120 milliseconds.
No. First, let us complete this thing about the low Earth orbiting first of all. So it is 6.6 millisecond or microsecond?
Sir,
Millisecond.
Millisecond. Then for the medium Earth orbiting,
So about 0.13 seconds.
Yes, sir.
what?
0.15 seconds.
135 seconds.
Try to use the same units. Try to use the same units so that you know the comparison becomes easy.
Sir,
If you
134.
are saying in millisecond, then do that. Then tell me the results, all the results in millisecond.
Okay. So 134.6 milliseconds.
154.6.
134.
134.6.
Sir, the last one is 238.6.
Millisecond.
230.
9 millisecond.
238.6.
Okay, let us say 238.6. So, I mean, this is a very easy calculation to do. I think everybody will be able to do this. Now, the point that I want to impress upon you is that now please calculate the amount of, I mean, the distance which is traversed by an electromagnetic signal, a radio signal, in this time, the distance which is traversed. In 6.6 milliseconds, it covers a distance of about 2,000 kilometers, right?
Yes, sir.
So, what we can understand that what is the level of precision required while maintaining time in case of satellite communication. That means if we are off by say 1 millisecond, I think that will amount to how much? 300 kilometer, close to 300 kilometer of distance. In 1 millisecond, what is the distance which is
Yes, sir.
covered?
It's a 300 kilometer.
300 kilometers. So imagine, even if you are off, even if you are your time measuring system is inaccurate by 1 millisecond, so that will mean that you are completely off the desired target by about 300 kilometer. Okay, that means while pointing the downlinking signal towards, say, for a low Earth orbiting satellite or any kind of satellite, if there is an error of 1 millisecond, it means that your downlinking beam, the beam which you want to be received by your receiving uh, base or your user base, that will be off by 300 kilometer. So suppose instead of Kolkata, that beam will point, suppose 300 kilometer from Kolkata is like maybe Baharampur or something, if we are going to the northeast. So that means you can understand that the user base in Kolkata, that will not be receiving the signal, but inadvertently that signal will be received by some other users who are about 300 kilometer away. Okay, so this error could be both in the horizontal plane as well as in the vertical plane also. So what we can understand is that, did you get this point? That means because the round trip travel times are of the order of maybe few to a few hundreds of milliseconds. So, and because these signals are traveling with the free space velocity of light, an error in time measurement by even 1 millisecond, that may result in the some kind of an error in satellite communication. We will understand what kind of error will be later on, maybe towards the end of the course, how these millisecond order accuracies matter. So there will be some kind of an error which will be of the order of a few hundreds of kilometer, maybe. Okay, so there is a very high level of precision required in case of satellite communication, because we are dealing with signals which are traveling at a very fast rate. In 1 millisecond, the signal is traversing like 300 kilometers. That means in case of satellite communication, uh, accuracies of the order of seconds or minutes do not count. Okay, we are now entering into a new domain of application of radio waves or radio signals, where, contrary to our common understanding, that is, okay, my watch is running a few seconds or a few minutes, we do not bother, even if it is a few minutes, like 10 minutes or 15 minutes here and there. But here we are talking about an application of radio signals where even 1 millisecond, or for that matter, even zero point 0.1 millisecond matters, because 0.1 millisecond means about 30 kilometers. Okay. So in some kind of very specific applications, okay, mostly near the, the international borders, the military applications, there you have to be very precise, because 30 kilometers here and there may mean the difference between one country and the other country. That means instead of one particular country receiving your signal, there may be another country 30 kilometers away from the border who may be receiving the signal. So depending on the kind of applications that we are handling, even an accuracy of zero point 0.1 millisecond is extremely important. Now, The look angles in case of in case of satellite communication, they are usually the coordinates to which an earth station antenna. By the way, by an earth station we mean the receiving antenna system as well as the transmitting antenna system. And nowadays, the concept of a very large earth stations has almost completely vanished, because your mobile phone, that could also be a kind of a uh, small earth station. And nowadays there are even smaller sized earth stations, the size of a maybe the nail of your thumb. Okay, the size of the nail of your thumb. Even you have earth stations which are capable of receiving signals from satellites which are of that size, and they are present and operational in our department itself. So in future, if someday if you happen to come to the department, you may actually see those kind of ultra small size transmitters and receivers which are capable of receiving signals from satellites. We are not talking about transmission across a few meters or a few feet, but instead we are talking about reception of signals from satellites which are at least 20,000 kilometers above the surface of the Earth. So, the coordinates to which an Earth station antenna must be pointed, that means the direction in which your antenna for receiving the signal must be pointed, that is commonly known as those coordinates are commonly known as the look angles. That means, in case of these applications, you will find some of the terms or definitions which are very simple to understand, because they have been designed by engineers, not physicists. So that is why you can expect very simple kind of terms and definitions. Look angles. That means the direction in which I should look. My antenna should look. By looking, we actually mean that they are trying to look using or trying for looking for radio signals, not optical. So the coordinates are usually, they could be a pair like azimuth and elevation, or right ascension and declination. But that right ascension and declination is commonly used for radio astronomy applications, not so much for satellite communication. So we had defined already the right ascension and declination. So for radio astronomy signals, or for signals where they are trying to receive signals from radio stars, they use that kind of a convention. But it's all the same, more or less the same. Then, in case of satellite communication, of course, we use the elevation and the azimuth. Now, there is another point, another definition which we should know, which is known as the subsatellite point. So, the formal definition of this subsatellite point is that if you join the center of the Earth with the satellite, then the point on the surface of the Earth through which that line passes. You are joining the center of the Earth with the satellite. So, the point on the surface of the Earth through which this line passes is known as the subsatellite point. So that means, suppose this is the surface of your Earth, and suppose there is another layer. We are not going to talk about this in this course, which is the lower height of the ionized atmosphere. Below that we have the neutral atmosphere. So if this is the satellite from which the Earth station is trying to receive signal, Then, when you join the center of the Earth with the satellite, then the point on the surface of the Earth where it penetrates. So that point is known as the sub-satellite point. Now, the sub-satellite point is important to remember. I mean, this definition is important to remember because this is used in a lot of cases of satellite communication. So, moving ahead, when we try to define the two coordinates which are commonly used in case of satellite communication, namely azimuth and elevation, so here also we should try to understand that what they actually mean, just like we understood right ascension and declination. So here, if you take a look at this figure, suppose this is the center of your coordinate system, the origin. This is a local vertical. And this could also be, the location of your antenna, okay, at the center. Your antenna or the receiving antenna is located at the center. That's the local vertical. This is the east direction from your location, and this is the north direction. And this is the satellite whose signal you are trying to receive. So, if you join your location with the satellite and then you drop the projection on this plane which contains the east and the north direction, because that is your local horizontal plane. This is the local vertical. So if you move eastward from the north direction until you reach the projection of this satellite on the local horizontal plane, then that angle through which you are moving, it refers to the azimuth. And from the azimuth, as you move up, because a satellite cannot be in the local horizontal plane, it always has to be up in the sky. So as you move up through a certain angle, then that angle is referred to as the elevation. As you move up and reach the path or the line joining your location, your antenna with the satellite, then that angle defines the elevation angle. So with this definition in place, so that means with this definition, this is what is written over here. It is the angle measured eastward from the geographic north. See, the angle measured eastward towards the east from the geographic north to the projection of the satellite path on a locally horizontal plane at the Earth station. This is the local horizontal plane. This is the projection of the satellite path. So you join that with the center of the Earth, from the Earth station until you reach that projection point. Then that angle through which you have to move towards the east from the north direction, that angle defines your azimuth. And the range of azimuth, as you can see, that means that it could be from 0 to 360. As I was telling you, that as you go to the roof of your building and look up, then there are 4 directions in which you can turn yourself: the north, the east, the south, and the west. going in a clockwise direction. So the total azimuth range is from 0 to 360. And elevation is the angle measured upward from this horizontal plane to the path joining the Earth station. So the angle measured upward from this particular horizontal plane, to the path or to the line joining your Earth station with the satellite. So that angle is referred to as the elevation. So in case of elevation, we can understand that theoretically the range could be that an object is right on the horizon. So that means its elevation is 0 degree, or it could be vertically overhead when the elevation will be 90 degree. It cannot be anywhere outside this particular range. Either it is at the same level as you, that means in the same horizontal plane as the Earth station, or it could be vertically overhead, that means right above your head, and then the elevation will be like 90 degree. So in case of azimuth, the convention that is usually followed is towards the north you have 0 degree, towards the east 90 degree, then towards the south azimuth is taken as 180, and towards the west it is 270. Okay. So in the last class, I think someone answered my question that if we are trying to track a geostationary satellite signal from a location in India or from Kolkata, say, for example, then we have to point our antenna towards the south. Okay, because the geostationary satellites are all over the equatorial plane. They are always over the equatorial plane. So the equator is like 0 degree north, and we are about 22.5 degrees north in latitude, the location of Kolkata. So from Kolkata, if you are looking towards the south, then that means you have to point your antenna towards the south in order to receive the signal from a geostationary satellite. So now, can you tell me that in this diagram for the convention followed for azimuth, in which of the quadrants we are more likely to find the geostationary satellites? There are 4 quadrants you can see. One of them is this one, and the other is this one, and this one. So there are 4 quadrants. So in which of them can you expect to find geostationary satellite?
So the between south and east, the third, fourth, and the third.
Between south and east. That means between this one and this one.
Yes.
Okay. Why do you say that?
Basically, it's anywhere south, but
Yes, it's anywhere south, right? So,
I think it can be both. The southwest also can be. Yeah.
anyone else? Anyone else, please?
Sir, I think it is third and fourth quadrant as well.
Third and fourth. That means which one?
From west to south and south to east.
Okay. So why do you think that should be the 2 preferred I mean, that should be the more likely quadrants. Why do you think so?
Sir, because all the satellites are situated on the equatorial plane, and equatorial plane is situated across the Earth totally, so it can be on the west as well as east.
Uh,
Okay, so
Sir, I
what?
think in south
Yes,
is sir. If we think from the point of view of Kolkata,
yes.
I think southeast should be the answer.
Why? Why?
Because sir, so because I see the TV antennas are always DTH umbrellas are always pointed in the southeast direction. So I
In the
think they might,
southeast direction.
yes sir. So might be from our location, the satellite must be in a bit eastward direction.
No, actually, you see, it could be in any of these two quadrants. Okay. Theoretically speaking, the satellites, the geostationary satellites, they could have azimuth ranging from right from 90 degree through 180 to 270 because your Earth station is at the center. So looking south, you have both these quadrants where you can expect to find the geostationary satellites. So that will be, those will be the two quadrants. Now, depending on the service provider of your DTH, they may be tracking a signal from a satellite, which is like southeast of our location from Kolkata. But suppose if that same operator is, having services in one of the northeastern states, then they may be pointing towards the southwest. So normally we should say that it is south direction from Kolkata, where we expect to find the geostationary satellites. And the corresponding azimuth for that will be ranging from about 90 degree to 270 degrees. So depending on the location of the satellite, whether southeast or southwest, the azimuth will be accordingly mentioned. Now, sometimes what happens is that uh, because we have defined this subsatellite point, in case of geostationary satellites, sometimes only the subsatellite, that means when you mention that it is a point means that there has to be at least two coordinates associated with that. Okay. It may be a point, but that point will have, like, for example, any point on the surface of the Earth has got a latitude and a longitude. So corresponding to a geostationary satellite, it is said that suppose you have a geostationary satellite, whose coordinates are like, suppose 73 degree east. Okay, somebody tells you that I want to track the signal from a geostationary satellite, and I know that its coordinate, its subsatellite point is like 73 degree east. So suppose somebody gives you this problem that I want to set up a satellite communication link with a geostationary satellite which is at 73 degree east. So how will you proceed? Is this information enough? He will also tell you, that person will also tell you the frequency at which that satellite is working. But is this information enough to set up your antenna?
no, sir.
Why?
So we will need the elevation angle also.
No, that elevation we have to calculate. That is a separate
Okay.
thing that I will come. If somebody
Yes,
tells you that it is like 73 degree east, then is this information enough?
Yes, sir, it is enough because by default the 0 degree north is already given
Why? How
because
do you say that?
because it is a geostationary satellite.
Okay. It is a geostationary satellite, so that's why it will be always over the equatorial plane, right?
Yes, sir.
And that's why you do not have to mention the corresponding subsatellite latitude. Only if you mention the subsatellite longitude, then that will be sufficient in case of a geostationary satellite, because by default the subsatellite latitude will be 0 degree north. So coming to this figure now, if somebody tells you that we have to track a signal from a satellite which is at 73 degree east from Kolkata, then in which quadrant shall I point my receiving antenna? That geostationary satellite is having a subsatellite longitude of 73 degree east.
Sir, in southwest.
Southwest. Why?
Sir, because we are about 82 degree east. 82 is actually near Allahabad, so maybe
88
Kolkata, maybe 85.
88.
Anyone else? Can you answer this question?
So
That
since we are 88-degree east and north of that point, so I guess we have to point southwest. Sorry.
any of the girls, please? Paramita Banerjee, can you answer this question?
Sir. Yes, sir. I thought also southwest.
Why? Please explain your answer.
Um,
Hello, please explain your answer.
no, sir.
I mean, you are saying that southwest. Why southwest?
Because sir, angle is upward and 0 to 90 degree. So,
Huh? What?
no, sir, I can't.
Okay. Anyone else? Moushumi Mondol.
Yes, sir.
Yes, can you answer this question? We are trying to track a signal from a geostationary satellite whose subsatellite point is 73 degree east. So in which quadrant shall I point my antenna?
Sir, I don't see the particular coordinate because both the third coordinate and fourth coordinate are possible.
No, we have now specified the subsatellite point. We are not saying any geostationary satellite. We have mentioned a particular geostationary satellite whose subsatellite point is or longitude is 73 degree east. So now we have narrowed down. So now can you tell me in which quadrant, southeast or southwest? It will be south, that is okay. But in which quadrant, southeast or southwest? And why? So you are not following properly, I think. Just
Sir, I'm
attending
following, sir,
online.
but please
Yes,
understand this
please.
point.
See, a geostationary satellite will always be located to the south of your station. That is now clear.
Yes,
So,
sir.
if if we are trying to track the signal from Kolkata, so Kolkata is somewhere at the center of this particular figure. So it will be either southeast or southwest. Now, as somebody has already mentioned that the longitude of Kolkata is 88.5 degree east, while the sub-satellite point of this particular satellite is 73 degree east. It's an actual satellite which we track signals from. Okay, 73 degree east. So that satellite 73 degree east and 88.5. So that means that satellite is located to the west of our location. Okay, so it will be southwest. So that location will be somewhere in this particular quadrant. Now, of course, once we go through the calculation of elevation and azimuth, then we could further pinpoint what will be the exact direction in which the antenna, what will be the exact elevation and azimuth at which the antenna has to be pointed. And then suppose there are other satellites also, like one other satellite is at 96 degree east. So in case of that satellite, which is having a subsatellite longitude of 96 degree east, for that satellite, because Kolkata is 88.5 and the subsatellite longitude of that satellite is 96 degree east, so that will be east of our location. So that satellite will be located or having a azimuth which corresponds to this particular quadrant. That means from 90 degree to 180 degree. Is it clear now?
Yes, sir. Now I understand.
Okay. So moving ahead, let us now try to understand that how we can actually calculate the elevation and then the azimuth of a particular satellite. So suppose this is the geometry that we are following. From the center of the Earth, this is your Earth station. This is the satellite whose signal you are trying to track. And with respect to the Earth station, this is the local horizon. This is very important to understand that the local horizon will be different at different points on the surface of the Earth because of the curvature of the Earth. It will be different at different points. So, keeping that in mind, if we join the center of the Earth with the Earth station and also the center of the Earth with the satellite, the angle in between, let us define that as gamma. Then RE is the radius of the Earth and D is the distance from the Earth station to the satellite. And with reference to the local horizontal at the Earth station, this is your elevation angle. Okay. And the distance of the line, the distance between the center of the Earth and the satellite is RS. That means it includes the orbital altitude of the satellite plus the radius of the Earth. This angle gamma is often referred to as the central angle. Okay. So, according to an existing mathematical relationship, cosine of this central angle gamma, that means this central angle, can be expressed in terms of, the coordinates of the Earth station and that of the satellite. Like, for example, this capital LE, that is the Earth station west longitude. We have to remember that over here, all the longitudes which are expressed by capital L, they correspond to the degree west. That means they are expressed in so many degrees west longitude, and the corresponding latitudes are in degrees north. So this capital LE is the Earth station north latitude. LS is the subsatellite point north latitude of the satellite, of course. The small LE, that is the Earth station west longitude, and small ls is once again the west longitude of the subsatellite point plus sine of this LE sine LS. Okay, that means this central angle, it contains this expression for the central angle. This contains the Earth station north latitude, that means the latitude expressed in degree north, the subsatellite point north latitude, then the Earth station longitude expressed in degree west, and the subsatellite point longitude expressed in degree west. Then this distance d, this can also be expressed in terms of, in this triangle, which whose three sides are RE, D, and RS. This side D can be expressed as the square of this one side RE square, square of the other side RS square, and the product of these two sides with the cosine of the included angle. That means the central angle. So this is how it is expressed. That means this d square can be expressed as rs square plus re square minus 2 re into rs cosine of this angle of gamma. And from there, actually, if you take the square root and you take rs as the common, you get an expression which is something like 1 plus re by rs whole square minus 2 times re by rs cosine of gamma whole to the power half. Then the angle elevation, this angle elevation angle is nothing but this angle minus 90 degree, because you see this is the radius of the earth and that is the local horizon. That means the tangent at this point. So the angle between these two is 90 degree. So that means elevation is nothing but this whole angle psi minus this minus this 90 degree. So this is what is mentioned over here. And then this, once again going back to this triangle, those three sides are RE, RS, and D. We can write that that this RS by sine of the angle which is opposite to that. That means you see this is RS, and the angle which is opposite to it in this triangle is psi. So RS by sine psi will be equal to D, and the opposite angle is gamma. So it will be equal to D by sine gamma. These are all some standard, geometrical expressions that we are using here. So starting with the cosine of this central angle, then the distance between the Earth station and the satellite expressed in terms of the radius of the Earth and the distance of the satellite from the center of the Earth, and the cosine of the central angle. Then following the law of sines, we can also express it in this way. And so cosine of this elevation angle finally becomes, you can work it out yourself, and you can find that this cosine of the angle of elevation will be sine gamma divided by 1 plus re by rs whole square minus 2 times re by rs cosine of gamma whole to the power half. And by the way, I think in one of the earlier classes, somebody was asking about which book we should follow. So it is Pratt and Bastian, Satellite Communication by Pratt and Bastian. It's a very standard book, and they are available. A number of copies of that book are available in our departmental library, as well as I think nowadays you can also have the electronic versions of those books as well. Although I don't know where you can find the electronic versions. The hard copies are there in our departmental library. So you can come down any day and collect one of those copies. So most of the material that we will be talking about, you can find them in this book, Pratt and Bostian, Satellite Communication by Pratt and Bostian. So having understood or having accepted these, processes and equations that we use for calculation of the elevation angle. So suppose if I say that the Earth station at Kolkata, its latitude and longitude is 22.58 degree north and 88.38 degree east, and we are trying to track a geostationary satellite having a subsatellite longitude of 65 degree. Could you please calculate what will be the elevation? All these equations are in front of you. Just remember that in these equations, the longitudes are in degree west. So you have to convert them to degree east. I mean, if they are in degree east, you have to convert them to degree west before you put them in this particular expressions. So please try to calculate this now and tell me what will be the value.
So for converting it to degree west, we have to just add a minus, right?
No, no.
Um, 180
Just
degree.
Minus 360 degree.
Okay. Yeah.
yes. Just think about it.
Yeah.
How you convert longitude from degree east to degree west.
আমি নিচে যাব, এটা আপনাকে দেখে হ্যাঁ নিচে কাজ আছে, এটা দেখুন একটু উল্টো পাল্টা যাচ্ছে হ্যাঁ।
So won't we need the value of RS for doing the calculation for this?
See, this is a geostationary satellite. Of course, you can
Okay.
understand
Yep.
because
Yep.
so you just have the orbital altitude and the radius of Earth. You can put the radius of Earth as 6,400 kilometers. Yes, anyone? Have you finished? Amit Rakhar, have you got the value?
Sir, I'm calculating. Just one.
Okay, okay.
Sir, I'm getting, sir, I'm getting 49.9 degrees. Correct.
Elevation.
Yes, sir.
Let the others also give their values.
Yes, I also got near 50.
Okay. Ognisha, are you calculating?
Yes, sir.
Yeah, so tell me the value.
Yes, I also got around 50.
Around 50. Chirantan, have you got any value?
Yes, sir. I only told 49.9 degrees.
Okay. Yes, the actual value for the elevation of this particular satellite, this is once again also an actual satellite whose signal is received from Kolkata. It's around 52 degrees. So maybe that 2 or 3 degree difference is arising because you have taken the radius of the Earth as about 6,400 kilometers, or maybe the orbital altitude you have also made it around 36,000. If you put it more accurate values, or if you go to the higher decimal places, I think you will get a value of elevation which is close to this 52 degrees. That is 52 point something. That is the elevation for this particular satellite. It is its name is Inmarsat, International Maritime Satellite, and it's a geostationary satellite, and this signals from these satellites are regularly, routinely being tracked from Kolkata. So, in that last expression for the calculation, you see for a geostationary satellite, this subsatellite point north latitude will be 0. So, that term will simplify. So because of this ls being 0, so this entire second term, that will be 0. So basically you will be left with only cosine of this Earth station north latitude and this term, because this will be 1. So for geostationary satellite, some simplification does take place for that equation. Now, calculation for azimuth is a little bit more involved, and there you have to actually, calculate an intermediate angle before you can actually, go ahead and find out what will be the value of azimuth for that satellite. And depending on the value of that intermediate angle, you have to consider that whether your Earth station is in the northern hemisphere or in the southern hemisphere. And if in the northern hemisphere, then the satellite could either be southeast or southwest of your station. So this value of alpha, which is the intermediate angle, that essentially contains, you see, the contribution coming from the west longitude of the subsatellite point, as well as the west longitude of the Earth station and the north latitude of the Earth station. So from these values, you get a value of this alpha. And if your station is in the northern hemisphere and say the satellite is southeast of your Earth station, then the azimuth becomes 180 minus this alpha, which is the intermediate angle. And if the satellite is southwest of the Earth station, it becomes 180 plus alpha. And if your Earth station is in the southern hemisphere, then of course you see all these things that we had talked about, that locating a satellite with respect to India, that will reverse. Suppose geostationary satellite is being tracked from, say, Australia or South Africa in the southern hemisphere, then in that case, the satellites will be in either of these two quadrants because they are in the southern hemisphere, and so the satellite being located above the equatorial plane, the location will be either in of these two quadrants. So, for that case, when the Earth station is in the southern hemisphere, the satellite is northeast of the Earth station, then it will be simply alpha. And if it is northwest, then it will be 360 minus alpha. So now, could you quickly calculate the azimuth for that same satellite? You have already calculated the elevation. So now please calculate the corresponding azimuth angle.
So 231 degrees.
231 degrees. Let's hear the others. What value do they get?
228.796.
228.7. Anyone else? Anyone else? Please tell me the value.
So 228.236.
Okay, your name, please.
Sromana Mojumdar.
Okay. Yes, so the value of this azimuth will be around 228 degrees. So when we say it's around 228 degrees, that means that it is 65-degree east, so it is west of our station. So it will be located in this particular quadrant. So now we had started from a very general understanding that for tracking a geostationary satellite from a location in the northern hemisphere like Kolkata, the satellite could be located in either of these two quadrants in terms of the azimuth. And now we know that once simply the subsatellite longitude is given for that satellite, we can go on and the Earth station, of course, is mentioned. Then we can go ahead and calculate what will be the exact elevation and the azimuth of that satellite. So for this particular satellite, which is at a subsatellite longitude of 65-degree east, we found that the elevation is something like 52 degrees and the azimuth comes out to be something like 228 degrees. Now, the next thing of interest for us to understand is that when we talk about receiving signals from a satellite, then does it mean that any satellite anywhere in space could be tracked from any location on the surface of the Earth? The answer is no. We can track satellites only from the general or the common sense. We can understand that we can only track satellites or receive signals from satellites which are above our horizon. We cannot receive signals from satellites which are below our horizon. I mean, not, not reliable radio signals when the satellites are below the horizon. So, that condition has to be, kind of consolidated into a mathematical relationship. And that mathematical relationship is governed by the visibility condition. I think we will go to this particular topic in the next class, and we will stop here for today. Now let me have your attendance, please. So just a minute. Today is 13th. Okay, 301. (301) is absent, right?
No, sir, present. So my mic was not working properly.
Okay. 302.
Present, sir.
303.
Present, sir.
305.
Present, sir.
306.
Present, sir.
308.
Present, sir.
309.
Present, sir.
311.
Present, sir.
313.
Present, sir.
314.
Present, sir.
315.
Present, sir.
316. 318. 318.
Sir, I am 317.
317. So you were
Yes,
not
sir.
present in the last two classes, right?
Yes, sir.
What's your name?
Sir, my name is Devraj Das.
Okay. 318 is absent, right? 319.
Present, sir.
320.
Present, sir.
321. 321. 322.
Yes, sir.
323.
Present, sir.
401. 401. 405.
Yes, sir.
স্যার আমি অনেক হালদার 402
হ্যাঁ
স্যার আমি অনেক হালদার 402
তুমি কি আগে ক্লাসগুলো করনি?
না স্যার
405.
Yes, sir.
407.
Yes, sir.
408.
Present, sir.
Sir, roll number 321 present. My data just went off.
321. Your name?
Ognisha Bhomik.
Okay. 411.
Present, sir.
420.
Sir, present, sir.
421.
Present, sir.
422,
Present, sir.
423,
Present, sir.
424,
Present, sir.
430,
Yes, sir.
431,
Yes, sir.
432, 432, 433,
Present, sir.
4, 435, 435, 437,
Present, sir.
438,
Present, sir.
439,
Yes, sir.
440,
Yes, sir.
441, 441, Shayan Dotto,
Sir, present. Present, sir.
Ravi Kumar Thakur,
Present, sir.
Sir, 442. I was absent for the last two classes.
442. What's your name?
Sir, Shagnik Sharnal.
Okay. Okay. Thank you.
Sir, roll 301, Deputy Ghosh.
301.
Yes, sir. Earlier, my mic was not working properly.
Okay.
Saram 414.
414.
Yes, sir. So
What's your name?
Shivam Kumar Sharma.
So you were not present in the last two classes, right?
No, sir.
Okay.
Sir, 435.
435.
Yes, sir.
Yes. So you are present. What's your name?
Sir, Ram Pravesh Kumar Gupta.
Okay. Okay. Thank you and see you on Wednesday.